Hi there. What we've got here this time is a heat radiation problem. So it's a heat transfer by radiation. Okay. In this case, the star Arcturus, one of the brightest stars in the sky, has a radius of that and a surface temperature of 4,290 kelvins. And we're going to assume here that the emissivity is 1. Okay. And we're going to ask a couple things here. What is the power radiated by each square meter of surface? And what is the total power radiated by this star? Okay. Now, as you might guess, this is a star. Okay. And so when we get to part B, we're going to have a pretty darn large number. Okay. So let's see how that works. So we've got heat. Basically, this is all about heat transfer by radiation. And so the mathematics that governs that looks something like this. Q over delta T is equal to sigma A E times T to the fourth, okay? Where sigma is the Stefan-Boltzmann constant, A is the area we're talking about of the surface, E is the emissivity, okay? That's basically this emissivity. It depends on actually it depends on how well the surface absorbs radiation. Okay, and so we're basically going to assume it's 1. It's a value between 0 and 1, and we're going to assume it's 1 here, meaning that if you shine a flashlight onto this star, okay, the star is going to absorb all the light from the flashlight. Okay, which is actually a pretty good approximation here. There's nothing in a star that's really going to reflect it. Okay, which is kind of the other option. Let's see, and finally this T to the fourth here, that is the temperature, and of course this has got to be in kelvins. Okay, so let's see what we've got here. All right. Let's see, we're trying to calculate the power radiated by each square meter. So power, that's what this Q over T is. And remember, power is energy divided by time, and that's what Q over T is. Q is, the energy transfer divided by time, okay, the heat per time. So sigma, that's our Stefan-Boltzmann constant, or as I like to call it, the 5678 constant. Let's see, watts per square meter Kelvin to the fourth. Okay, a lot of these constants are going to have weird units. The area, well, we want to know the power radiated by each square meter, so we're going to call this 1 square meter. Okay, our emissivity we're going to take to be 1. Our temperature in Kelvin is 4,290. And that's raised to the fourth power. And so Q over T, as a result, ends up giving us about 1.92 times 10 to the 7th watts. Okay? So, now that's our answer to part A here. Okay? And notice this is for 1 square meter. Okay, so on to part B. Part B wants the total power radiated by this star. Okay, we've basically calculated the power due to, that's emitted by 1 square meter of the surface of this star. So if we want the total power radiated, we just got to multiply that by how many square meters we've got. Okay, so let's do that. 1.92 times 10 to the 7th. Really, this is the amount of watts per square meter. And then we're going to multiply that by how many square meters we've got. And the area, this is the surface area of a sphere, which is 4 pi r squared. Okay, that will be on your formula sheet if you need it. Okay, so you don't have to worry about memorizing that, although it's a fact that everyone should know. So 4 pi times our radius, which is 1.77, okay, times 10 to the 10th meters squared, and altogether that gives us the whopping big number here of 7.56 times 10 to the 28th watts. Okay? That is one big, powerful light bulb.